they are totally different from the polar spacecrafts. The polar spacecrafts they are bigger and they are more complex. So you can imagine that two space agencies like NASA and ESA, one of them will go for polar, the other one goes for ecliptic, and they will be built in parallel. And they will be launched together, and they will operate as a whole, as a system together. And that's what I said when I said that we need everybody to come together to build this mission. So this mission is big, and it's expensive. So when you look at the cost of this mission, it goes, depending on how you want to do it, it goes from $2 billion to $3 billion, including everything. If you go to NASA alone, they might say it's expensive. But if we tell, let's say we have NASA, ESA, and potentially JAXA or other agencies, that will make it easier in terms of schedule and in terms of cost as well. And more than that, it brings all of us together. And that's really important. And the other thing, Firefly is a game changer. We need really a game changer, because when you look at the science we are doing, at least before probe and orbiter, there is some sort of stagnation in what we are doing. This one will change completely with how we look at the sun, its environment, in general. So, yeah. Thank you very much.
Questions, Milan?
No, when would be the, I mean, if you are optimistic, when would be the start of the nominal mission? I mean, the mission where the two spacecraft which passed by Jupiter.
Yeah. So, okay.
I saw that 20, 38, 39.
Well, it depends when the agencies, okay, it depends first of all from the decadal survey that we do every decade for NASA. The competition now is to get the decadal survey to rank Firefly very high, toward the top. That it becomes
is it competing with the interstellar probe?
Yes. If you look at all the mission concepts that were submitted to the decadal, the two big ones are interstellar probe and Firefly. These will be put in a category. They are flagship missions. All the rest will be in a different category. So the competition to Firefly is interstellar probe.
Okay, and then when will be the launch?
Well, if we are ranked high in NASA and ESA and JAXA and whoever want to be part of this, we go for it. We can start any time from 2025. Let's say if we start 26 or 27, it will take us about 5 to 6 years to develop the mission, and after that you launch it. And so the ecliptic will be operational right away.
Okay, and the two.
The other two will have to go to Jupiter, come back, and the idea we have to start circularizing the orbit. It's not like Ulysses, because we need to circularize the orbit to bring it inward. What we call a cruise phase, but it's not really cruise phase, because we are doing science during that period, except that we are not at the last orbit, but the ultimate orbit. That period will be something like a little bit over 5 years. And once we reach the last orbit, we have 5 years of full science.
So basically 2040.
Yes.
Okay, so I'm asking for the young people.
No,
so that they get ready, because
the launch will be something like, let's say mid-30s. That's, I would say it's probably even a little earlier if we go a little bit optimistic, but that's what we are looking for. So it's mid-30s, something like that. But obviously, after that, it's 10 years long missions.
Cool. All right, great. Thanks again. And yeah, now we start with the regular workshop program for today. Here's your microphone. Okay, does it work? Yeah. Cool.
Okay.
And the first talk of the regular session is by Shadi Salem about electric field turbulence.
It doesn't, yeah, it works. Okay. I'll talk to you about our work at Berkeley with several collaborators here, Luca, Daniel here, but also Chris Klein, Vadim, and on electric field fluctuations in the solar wind and why it's important. So we've seen a figure like this already a few times this workshop. You know that the solar wind does not cool adiabatically, it expands. You can see this from Helios data with the adiabatic evolution from the corona, well, from the, going down here. And this is the actual measurements of proton temperature. So local and extended heating is necessary. That implies turbulence and turbulent dissipation, and role, of course, of fluctuations and waves. And we know turbulence is ubiquitous in space plasma. We've been talking about it all week. So, but the question is, how is the energy dissipated? And that's still an unsolved problem. What are the various mechanisms? Whether it's wave-particle interactions, stochastic heating, or reconnection. How do they compete in all the parameter regimes of interest, and how is the plasma heated as a result? How much goes into the ions versus the electrons, isotropic versus anisotropic? And in this picture, the electric field is a key parameter in characterizing these mechanisms, and it's the agent linking fields and particles. So, yes. Sure. But it's I mean, we've seen figures here where the two. No, it's not starting at 0. It's starting at much lower altitude. It's starting at, so this is 10. It's starting at the orbit of PSP, the lowest orbit of PSP, 9 solar radii or so. That's where it starts. We can do it later. You'll see.
I think it's wrong.
It's just the.
Just a bit wrong, but
Okay. You take basically the same. So this is a fit, right? And so you take the same value here, and you follow the adiabatic evolution. Okay, but it's not the point of the talk. No. Okay. So. Recent observational and theoretical works suggest on turbulence and dissipation suggest that kinetic fluctuations are both heating and isotropizing the solar wind during its transit to 1 AU. And it's important that we understand the nature of these fluctuations and therefore the associated heating processes. So whatever the dissipative process that links fields and particles, whether it's Landau damping, cyclotron damping, stochastic heating, or energization through coherent structures, the heating and the acceleration occurs because of electric field fluctuations. So it's important to use these measurements and to constrain the nature of the fluctuations. So anyway, in the past, this is just to show a bunch of different studies using magnetic field, but the majority, like I said, of work studying dissipation range fluctuations involve analyzing magnetic field fluctuations, but not electric field, and B alone does not provide the full picture.
Sorry, McLean 2017, there is a very nice paper.
We're coming towards it. Okay. Yes, I know. So the first study that looked at electric field fluctuations was by Stuart Bale, where he looked at both the electric field and the magnetic field together, and his interpretation was that when he looked at the E over B ratio as a function of K rho using the Taylor hypothesis, that here you see this the data fits, it's well fitted by, is consistent with kinetic alpha waves prediction. So the question I had back then was that, okay, well, what if you don't use, so if we use Taylor hypothesis and the fluctuations are not necessarily kinetic Kelvin waves, they're whistlers or so, what happens? So that wouldn't be working. So a few years later, well, so just a few words about the Taylor hypothesis. So this is the Doppler shift relation, right? So the Taylor hypothesis assumes that this is much, much smaller than that. And people use this relationship to transform F into K and vice versa. But really, when you look at all the angles and some, it's a little bit more complicated than that. So later on, we did some work looking at a cluster interval in the spacecraft frame as is. So this is the power spectrum of B, and this is E here. And you see E reaches the noise floor at about 2 hertz or so, 2 or 3 hertz. And what we did is we calculated from linear Vlasov-Maxwell solutions what the prediction is going to be for quasi-perpendicular kinetic Kelvin waves in red and whistlers at different angles, parallel and then oblique. And then we transform those predictions into the spacecraft frame and compare directly with the data. That way you don't use Taylor hypothesis. So what we saw is that if you look at the E over B ratio, the data is consistent with quasi-perpendicular fluctuations. And then if you look at the magnetic compressibility on top of that, then you can really disentangle between kinetic Kelvin waves and whistlers because the green line is being the data follows the red predictions from quasi-perpendicular kinetic Kelvin waves. So, but what happens beyond 2 hertz or so? So we need data up to the electron scales. So we started, a few years ago doing these, analyzing electric field and magnetic fluctuations from Themis and Artemis. That provide high time resolution magnetic field and electric field as well as density fluctuations up to 8 kilohertz. And I'll just go faster. So this is one example here where you see the raw measurements in the spinning frame of the spacecraft. And this is one of the best intervals. You see that this is B here. No, this is electric field. So you see this is E12, E34 are in the ecliptic, and then that's the vertical axis, E56, which is unusable. But you want that wave here, that measurement, or the signal to be as sinusoidal as possible. And that's here just as a comparison. This is B. And this is 1 minute of data. So it's important because the signals, the electric field signals are very, very polluted by lots of various signals, and sometimes they're very difficult to correct. But this is one of our best intervals. So it's an interval where you see this is 2 hours here of data. The fast survey mode, so we have different modes. The fast survey lasts 35 minutes, and it's limited by these lines. Then the particle burst is 5 minutes. It's between these 2 red lines. And then the wave burst, 16 seconds of data, is here in the middle. And these are the different characteristics of this interval: beta, proton beta of 2, electron beta small of 0.3. So if you calculate the power spectrum of the magnetic field, you see that here. And the black is the wave burst, the fast survey. Blue is the particle burst, and then the red is the wave burst data. And you see that this is the noise floor here. The noise floor for the magnetic field fluctuations is reached about 40 hertz or so. This is the electron cyclotron frequency for this interval, lower hybrid, and these are FCEs, electron cyclotron, ion plasma. And these are the various frequencies corresponding to K rho of 1, K lambda I of 1, etc. So the slope of, the magnetic field is uneventful. It's as you see it elsewhere, many other places, like the magnetosheath and so on. The slope here is minus 2.77. Where? of frequencies here, I mean, of intensity. So I'm saying that you reach about the noise floor here where it's about 3, a factor of 2 to 3 here, okay, at 10, 20, well, 10, 20, 30, 40, 50 even or so hertz. That's the noise floor, okay? Okay, for B. But when you look at the electric field, well, before we get there, I'm a little too fast. So if you look at the B parallel over B ratio, like we did for cluster, you see that same similar behavior, which, you know, makes you think of, again, characteristics of kinetic Kelvin waves. But if we look at E, you see lots of features. So the electric field fluctuations measured all the way to here. So you reach, this is the sum of the shot noise plus Johnson-Nyquist noise, and then the digitization noise. You see that sum here. And you reach it at 100, 200, 300, 400 or so. And so you see different features in the spectrum. You see the inertial range here. Then you see a steeper power spectrum, and then a flatter power spectrum of minus 1.4, and then another steeper power spectrum, and so on. So what's happening? So it's, you know, comparing it to the magnetosheath where, you know, I'll get to the next slide, comparing to the magnetosheath. No, this is one interval, but a different, again, the black is the fast survey, 35 minutes of data, and then embedded in it, it's the particle burst. I forget, 15 minutes, a few minutes of data, and then the wave burst, which is 16 seconds of data. The higher frequency, yes. No, it's, look. The total interval is here, the 35 minutes, right? So you take that for the fast survey data, then the particle burst, the 5 minutes is embedded in it here, and then the wave burst is in the middle. So they're what's the English word? No, it matches. It's the same electric field. Okay, so this is the fast survey waveform, right? This is the particle burst waveform. It's the same waveform. What do you mean? Yes, this is one of the best intervals. This is in the spinning frame of the spacecraft. Then you de-spin. Then you de-spin. You look at this to look at how the quality of the signal. If this, in many cases, the signal is not sinusoidal, it's triangle or some. It's very polluted. Yes. Then you remove the spin and you go into the X and Y. Okay. Well, I'm not even halfway. So, okay. Where? Here. Yes. It's just here, just between there and there. I knew this was gonna be this. I knew this was coming.
No, it's from low hybrid to FP. You can just use one function.
Okay, we'll do it later. Yes. Okay. Let me move on, please. Okay. So now, if you look at the E over B ratio, E over B. So in the magnetosheath here, 2 different studies, one by Lorenzo and one by Christian, with 2 different spacecraft, find exactly an electric field that falls off as f to the minus 0.8 in the dissipation range. So in the solar wind, we find this, as I showed you. So that gives you an E over B that goes as f to the 1.4. So why is that? So the 0.8 is what you find, and in general, when you do simulations or so, and being consistent with kinetic Kelvin wave theory, so the interpretation, and thanks to Luca here for working with me on some of the interpretation of that. So this is the Ohm's law. So the total electric field is the sum of these different terms, the MHD scales, MHD term and Hall term and electron pressure term. So it's about the balance between all of these terms. And there are different ways of providing this balance. So do we have electron, so are the fact that we don't find, so in the hybrid codes, simulations we tend to find exactly that, what we see in the magnetosheet, the 0.8 slope. And why the discrepancy? So the electron inertia are not captured by the hybrid model, but as Luca is showing here in his paper in preparation, he might talk about this later, is that no, the agreement between hybrid and fully kinetic simulations with the same plasma conditions exclude this explanation. You see this where the dashed line and the solid lines are very comparable all the way up to the electron scales. Then another possibility is that there is a non-negligible time variability of the spectrum, maybe, but I looked at this also in the data and it's not an option. So, and then it's just a different balance of these different terms. And I want to move on very quickly because I'm going to get to the end. But we can talk about this when Luca is giving a talk later. Another explanation, so if you do, this is a 2D peak simulation. And so what seems, these are the power spectrum of B and E. And this is E over B. And you can see that in some range, you can get a slight flattening here. And that the simulation shows that this flattening is somewhat correlated with intermittency, as seen on PDF increments at small scale. So is this flattening due to maybe some degrees of intermittency that's higher at these scales, which would explain a steeper electric field? What can linear theory tell us? Just really quickly, I wanted to say if you plot the E over B ratio in the plasma frame using this expression where you remove the V cross B, and you calculate the expectation from a kinetic Kelvin wave at 88 degree or a Whistler at 10 degree or the Ein-Bernstein mode for this particular interval at 89 degree, you see these three predictions in that frame here. So the yellow are the Whistlers, the blue is the Ein-Bernstein waves, and the kinetic Kelvin was shown here. So somehow the kinetic Kelvin wave total electric field doesn't explain the observed E over B, but you see that maybe you end up with a really strong or some contribution from these two different modes. So maybe the delta E total that we measure